Objectives. I'd like for the following sentences to describe you by the end of this video. I can explain why the Lyman convergence limit gives us the ionization energy of hydrogen. I can calculate the energy of a photon from its frequency, or a mole of photon. So I can go from frequency to energy. And lastly, I can go from wavelength to energy of a photon. Fairly simple. So let's get started. The first thing we need to understand is, what is ionization energy? Here's a quick visualization of that. So we have a hydrogen atom here. Hopefully you recognize this. We have a nucleus and an electron orbiting that nucleus, or in an orbital around that nucleus if you like. Okay? And remember that there are a bunch of converging energy levels that this electron could occupy. So in theory it could jump up here or up there, okay? And notice that they're converging, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, they go up and up and up, but they're converging to some point which we call n equals infinity. Now if we add heat or any sort of energy to this electron, it can jump to high energy levels. It can jump to 2 or 3 or 4 or 5. Okay? If we add enough heat, or if the electron takes up enough heat, it jumps from an n of 1 to basically an n of infinity, which doesn't really exist, but we can still think about it as existing. So it jumps basically to n of infinity, and if it makes that jump, it's basically now left the atom. And what do we say of this atom? It has been ionized. We've gone from a neutral atom, that's a proton and an electron, to just a proton, or a hydrogen positive ion, and we've lost the electron. The energy needed to ionize this hydrogen atom, that is to move the electron from n of 1 ground state to n of infinity, is indeed the ionization energy. So then we define the ionization energy as the minimum energy needed to remove an electron from an atom to form an ion. Now typically we do this in the gaseous state because we standardize it that way. If you did it in liquid or solid, it would be slightly different. So we talk about a gaseous atom, okay, being energized to form an ion, and that's ionization energy. We can get this ionization energy from the spectrum of an element, the emission line spectrum of an element. We're looking at hydrogen in this case, so let's look at hydrogen's emission line spectrum. Hopefully you will already recall this picture that I'm going to show here from our previous video. If you haven't watched that video on emission line spectra, please go watch it. In that video we had explained that hydrogen spectra, or spectrum rather, is broken up into these series that converge towards higher frequencies. We have the ultraviolet, the visible light, the infrared, and on and on. For the purposes of the IB, you only care about the first 3, and you don't really care about these names. They'll never hold you responsible for those names, although they might mention them in the exam, but they won't ask you a question about them. This goes on and on, but the important thing is that the ultraviolet series is generated by electron drops from higher energy levels to the base, to the ground state, an n of 1. The next one, visible light series, or the Balmer series, is n of 2. The next one, n of 3, n of 4, and so on and so forth. We're going to focus on that ultraviolet Lyman series to visualize in a bit more detail the convergence limit. I think I've gone through a similar animation in a previous video, so this should look familiar to you. What we need to remember is that a photon is a light packet which is emitted when electrons fall down. It's a wave particle. So it's both a wave and a particle. It's the smallest unit of energy. Okay, so photons are going to be emitted when we fall down to lower energy levels. We're going to direct those photons to a prism. We're imagining now that we're inside of a spectrometer. Okay, so we direct the photons to a prism. Okay, and that prism will bend the photons more or less depending on their frequency. Specifically, higher frequency will be bent more than lower frequency, and therefore on that sensor there we end up with lower frequency lines at the bottom and higher frequency lines at the top. So let's get started. We heat this bunch of hydrogen atoms. For some of the hydrogen atoms, the electron will absorb enough heat to jump to an n of 2. That's fairly unstable, so it will tend to fall down and release light, creating that line there on the emission spectrum. For others of the hydrogen atoms, the electron will absorb enough heat to jump to NF3, fall back down, and create that line there, NF4, and so on and so forth. And we can see then that the lines start to converge. And the point at which they have converged is what we call the convergence limit. And that convergence limit corresponds to the distance here from an n of basically infinity, the last possible energy level the electron could occupy, a drop from that point to the ground state and n of 1. So this distance here. And this distance here, if we flip it, corresponds to what? The ionization energy. Because remember, the ionization energy was the energy needed to take the electron from a ground state to the n of infinity, which is to kick out the electron. And that convergence limit is equivalent to the energy drop from that kicked out position, the just kicked out position, back to the ground state. So hopefully now we've covered this objective. I can explain why the Lyman convergence limit gives us the ionization energy of hydrogen. Here's the reason in a nutshell. So it says that because the frequency at the convergence limit, that's there, okay, corresponds to the energy given out when an electron falls from an n of infinity here down to an n of 1, the ground state. And the ionization energy is the flip side of that, okay? It's the move from the ground state to the n of infinity, just outside the atom. So we're done with that one. Let's look at these next two now. So basically in this one we've covered how is it that the frequency of the convergence limit can give us the ionization energy. Now we need to actually calculate the ionization energy given frequency. But we won't only calculate ionization energy, we'll calculate just any energy when given frequency. And secondly, we'll calculate energy from wavelength. So let's get started. We had stopped at this point, and we had demonstrated how that convergence limit corresponds to this ionization energy. But we can actually measure the convergence limit, or physicists can measure it, I can't, in terms either of the frequency or the wavelength. Okay, so the frequency of the convergence limit for the Lyman series of the hydrogen emission spectrum is 3.28 times 10 to the 15 hertz. And the wavelength of that point is 90.1 nanometers. One question is, what are hertz, or what is hertz? It's a unit, of course, but what kind of unit is it? 1 hertz represents 1 cycle per second. So if I'm tapping you at 1 hertz, bap, bap, that's 1 cycle per second. This is a 1 hertz slap. Okay? And this is a 2 hertz slap, 2 times per second. Okay, so 2 times per second is the same as 2 second inverse, like that. Okay, so 2 hertz is the same as 2 times per second. This will be relevant in a second. So if I'm slapping you at 2 hertz, that's what it looks like. Now, if I were slapping you at 3.28 times 10 to the 15 hertz, that's equivalent to 3.2 quadrillion slaps per second. Okay, so you can imagine that the wave that corresponds to this convergence limit is cycling extremely quickly. Okay, so that is what hertz are, or what hertz is. You already know what nanometers are. 10 to the negative 9 meters. Okay, so we can use now either of these values, the frequency or the wavelength, to calculate the energy. All we need is a constant, a very special constant. Here's an analogy with constants so you understand what a constant is. If we know the radius of a circle, all we need is a constant, 2 pi, or just pi if you like, or tau if you like, tau, and we can find the circumference. So we just need the radius and the constant, we can find the circumference. If we have a bunch of sugar cubes, we know there are 25 sugar cubes, we're trying to find the weight of this bunch of sugar cubes. All we need is a constant, the weight of 1 sugar cube, and we can find the weight of all of them. Okay, so there's a constant. This is not quite a constant, but it gives you the idea. All right, now if we have a bunch of electromagnetic radiation, a bunch of photons, and we know their frequency or their wavelength, their frequency for now, then we can use something called Planck's constant to calculate the energy with that relation there. Energy equals Planck's constant times frequency. Energy equals Planck's constant times frequency. If we're given the wavelength, there's a way we convert wavelength to frequency, and then we can find the energy. Here is the man himself, Max Planck, okay, pictured with some people I think you're starting to recognize, Niels Bohr there from the Bohr atom. Pauli's exclusion principle. Who else? Einstein, of course, Einstein. Marie Curie, Schrödinger, maybe you know. Okay, anyways, we were saying that we can use Planck's constant, thank you Max Planck, and to calculate the energy of a photon given its frequency. So this now is the kind of question you will get on your IB exam. Given that the convergence limit in the Lyman series for hydrogen at that point there is 3.28 times 10 to the 15 hertz, calculate the ionization energy for an atom of hydrogen in joules. Very simple. Here are the steps. We use E equals h mu to calculate the energy in joules. What is mu? Mu looks like this. Okay, it looks like a V. It's a Greek letter, of course, and it stands for frequency. So mu for frequency. You can think maybe of a cat that likes to say mew, mew, mew at a high frequency. I don't know. Okay. Anyways, we can use this formula now to find the energy. It's quite simple. We plug in, well, first of all, we can get that formula from the data booklet, yes? So in section 1 of your data booklet, you have a bunch of formulas. E equals h mu is one of them. And we have a set of physical constants in section 2 of your data booklet, from which we can extract what? Planck's constant. So 6.63 times 10 to the negative 34 joule seconds. A very tiny number. And we multiply it by our frequency there, which is a fairly large number. And we get out a final value. Remember that hertz is the same as inverse seconds, which means that if we take Planck's constant, what's the unit of Planck's constant? The unit is joule seconds. We multiply by inverse seconds. Seconds cancels out inverse seconds. And we're left with what? Joules. And hopefully you know that joules is a unit of energy. So we have the energy. Nice and easy. It's beautiful. But you might not be asked to find it in joules. You might be asked to find it in kilojoules per mole. It's more likely, actually. So how do you do that? You convert from joules to kilojoules first, of course. How do we do that? We use what's called a conversion factor, or you could just divide it by 1,000. But if that's not intuitive to you, I recommend highly this conversion factor approach. What do you do with the conversion factor approach? You write an equality. What's an equality? An equality is an equation. So we write 1 kilojoule is equal to 1,000 joules. This is an equality, right? Yes. So we turn this into a ratio, or into a fraction. 1 kilojoule over 1,000 joules. Okay? And we're going to multiply this number here that whose units we're trying to convert by this equality, choosing the orientation based on where we want to go. What do I mean by that? So let's test out, let's put, for example, 1,000 joules on top and 1 kilojoule below, and try it out. So joules will multiply by joules to give you joules squared over kilojoules. That's not where we're trying to go at all. So we try the other way, and now we see that joules cancels out joules, and we end up with kilojoules on top. So that tells us we need to divide by 1,000. Okay, so we can plug that straight into our calculator. So we do that then, and we end up with that number there. Of course, all of this should be done on your calculator. If you have a Casio, it will be easier to put in all of these fractions. If you have a TI, well, you should get a Casio. Then we have now in kilojoules, we need to multiply by Avogadro's constant in order to scale it up to kilojoules per mole. So this is the amount of energy it would take to get a single electron and kick it out of the atom. But what we're interested in is a mole of electrons, or a mole of hydrogen atoms, which is a much more substantial quantity of atoms, or a much more substantial quantity of energy. So therefore we need to multiply this value here by Avogadro's number. Where do we get Avogadro's number from? Of course, from your data booklet. Or actually, this one by now you should have memorized it. 602 times 10 to the 23. And that gives us our final value there of blah, blah, blah kilojoules per mole. Nice and easy, right? It's not too hard, I promise. Okay, so what we've demonstrated now is that we can take this special line here, this convergence limit, if we know its frequency, and we can find its energy. But we can do for any line, we don't need that special convergence limit line. For any line here, if we have the frequency, we can calculate the energy. So let's look at an example there. Another possible question on the exam. It says the red line in the Balmer series has a frequency of 4.58 times 10 to the 14 hertz. Calculate the energy in kilojoules per mole of a mole of photons emitted with that frequency. This one, you have the tools now to do it on your own. So I recommend you pause the video and try it out. In 3 seconds, I will walk you through the solution. It's not too difficult at all. Okay, here are the steps. You just do E equals h mu, and then you do some unit conversions. 3, 2, 1. Here it is. E equals h mu, like I said. H is what? Planck's constant. Mu is your frequency, mu, 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 remember? And we get it from the question. So E equals, therefore, Planck's constant from our data booklet times that from our question. And we end up with that value in joules. But they're asking for it in kilojoules per mole. So we have to convert to kilojoules using our conversion factor. This number should get smaller. So instead of 10 to the negative 19, now it's 10 to the negative 22 kilojoules. And then we multiply that by Avogadro's constant to get our final value of 183 kilojoules per mole. Nice and easy. We're done now with our second objective, which is that we can calculate the energy of a photon or a mole of photons given their frequency. How do you do this? You use E equals h mu, where h is Planck's constant, mu is the frequency of the electromagnetic radiation, and energy is the energy. And then we need to change the units sometimes from joules to kilojoules per mole. Let's look at this last one of wavelength. The reason we can do this is the following. At a given speed, frequency and wavelength are proportional. You know this already. So if I show you these two waves, you know that this one is what? Low wavelength, high frequency, right? The distance between the crests is small, therefore it has a low wavelength. And if you imagine these as slaps, let's say each crest was a slap, and this would be high frequency slaps. So these are high frequency, there's a high frequency waveform there. And there we have a high wavelength, a large wavelength or a long wavelength, and a low frequency. So if those are slaps, they would come a bit more slowly at a lower frequency. Okay? And the distance between those slabs is quite wide. This relationship is captured by the following relation. C is equal to mu times lambda. Okay? What is C? C is the speed of light, or the speed of any wave being considered. But here we're talking about electromagnetic waves, so we use the speed of light. Mu, of course, is frequency. What is lambda? Lambda is the wavelength. It kind of looks like it represents wavelength, doesn't it? Looks a little bit like an L if you really try hard, and it looks like a wave also if you try hard. So wavelength there is lambda, another Greek letter. What we can do is we can take that expression, if we divide both sides by lambda, okay, then we cancel out that lambda, we get that mu is equal to C over lambda. Mu equals C over lambda. And then we plug in the value from mu into E equals h mu. So we replace mu with C over lambda, giving us what? E equals hc over lambda. Pause the video and make sure you can do that conversion there, because you will need to do it on the exam. Where do we get C from? The speed of light. You don't have to memorize it. It's in your data booklet. 3.00 times 10 to the 8 meters per second. Very fast. So let's use all of this now to do a question. The red line in the Balmer series has a wavelength of 654 nanometers. Calculate the energy in kilojoules per mole of a photon with this wavelength. Here is the idea. If you're ambitious, you could try this one just without me showing you, okay? So first you use this guy here, this relation, or this, I keep saying relation when I mean equation, C equals mu lambda to find the frequency, okay? And then we plug that into, we plug in the frequency we found into this expression, and we get our energy. We can get both of these formulas from our data booklet, and we can get all the constants that we need also from our data booklet. So let's try it. So we have E equals hc over lambda, which we derived on the previous slide. We plug in h, which is Planck's constant, from there. We plug in c, which is the speed of light, also from there. Okay. We plug in our wavelength from the question, and we're done. No, we're not done, right? Why aren't we done? Because here we have meters, here we have nanometers. You can't do that. That's a conflict of units. So we need to either convert this guy to nanometers per second, which is harder, or we can convert nanometers to meters, which is slightly easier because there's more space on the bottom of the fraction. So let's do that one, 654 nanometers to meters. We need, of course, a conversion factor. Okay, so you should know, hopefully one of your math teachers has made you memorize the fact that 10 to the negative 9 meters is a nanometer. And 10 to the negative 6 meters is a micrometer. Nano and 9 you can remember because, I don't know, 9 looks kind of like nano, right? 2 N's and then 2 vowels in between. 9 and nano. And then 10 to the minus 6 meters is also kind of small, not as small as a nano. You can remember that by thinking that you use a microwave at 6 a.m. and 6 p.m. 6 a.m. in the morning and 6 p.m. in the evening, right? So 10 to the negative 6 is 1 micrometer. So we take this expression here, this relation, 10 to the negative 9 meters is equal to 1 nanometer. We turn it into a ratio, okay? And we multiply that ratio in whatever orientation we need by our value here to get to what we need. That's just what I just said. So we multiply this by, we have meters on top and nanometers below, which allows the nanometers to cancel. We end up with what? Meters. So if we do all of that, the units will all cancel. It's quite beautiful when you do it. The nanometers cancels out the nanometers. The meters cancels out the meters. The seconds cancels out the inverse seconds. And we're left with joules, which is what? Energy. So we have the energy of this series. Sorry, not of this series, of this red line. The energy of those photons that comprise the red line. We have them, of course, in joules. They want it in kilojoules per mole. So we go through the motions. We convert first to kilojoules. And then we multiply by Avogadro's number to get the answer in kilojoules per mole. Here's one question for you to try. I'll give you, let's say, 3 seconds to pause the video and try it. 3, 2, 1, pause. I hope you've paused. Okay, here's the idea here. Okay, we're simply going to take energy equals h mu, plug in our h, our Planck's constant, from our data booklet, plug in mu from the question, and we have a final answer there in joules. Nice and easy. Extremely easy. I think a similar question to this actually came out on one of the recent papers. So don't underestimate how easy they can get. Huh? If you fail this kind of question, you have only yourself to blame. Okay, here's another one. Calculate the energy in kilojoules per mole of a mole of infrared photons with that wavelength. So pause the video again and try this one. In 3 seconds, I will reveal the solution. 1, 2, 3. Here we go. So we use E equals hc over lambda, which you can derive based on these two formulas. If you've forgotten, rewind the video and go watch it again. We plug in Planck's constant from where? From our data booklet. We plug in C from where? From our data booklet. We plug in lambda from where? From our question, 1.315 micrometers. Remembering to multiply by this ratio in the right orientation needed to get to where we're going. Where are we trying to go? We're trying to have this be in meters and also that in meters. So we need to cross out the micrometers. And you remember that 10 to the negative 6 meters is 1 micrometer because you tend to eat microwave food at 6 a.m. and 6 p.m. in the evening. So now we multiply all that out and we end up with what? Joules, a value in joules. They want it though in kilojoules per mole. So first we have to divide by 1,000 to get it in kilojoules. And then we multiply by Avogadro's number to get it in kilojoules per mole. I think, ladies and gentlemen, we are done with this math-heavy topic. To be honest with you, they don't ask that many questions on these calculations in the exam. So if you're feeling lazy, you could choose to just skip it in terms of studying. But if you're aiming for a 6 or a 7, then of course you cannot skip anything. But there's going to be practice, of course, on the website. And I will see you in the next video. Bye-bye.